with the second talk today. We have now Hadji Yaya Tall. He was graduated from, I can't pronounce, Sheikh Anta Diop University.
Yes, thank you.
Okay, from Dakar in 2012. He is from Senegal. And he got his master's degree at ICTP from Trieste in 2013, and his PhD at IMPA in 2018. And now he is a postdoctorate at IME, the University of Sao Paulo. And today he's going to talk about one on a spectral theory of Shrödinger operator with dynamically defined potential. Yeah.
Thank you, Adriana. Thank you so much. I'm very happy to be here. And I would like also to congratulate you for the conference. So it has been great so far. So today I'm going to talk about the spectral theory of Shrödinger operator. So the idea is to develop tools from ergodic theory and see how these tools could be applied to the spectral theory of Shrödinger operator. So first of all, let me talk about the linear cocycle. Luciana has mentioned linear cocycle and the Lyapunov exponent in her talk. So I will be very brief. So let's start. So linear cocycles, to define linear cocycle, you need two data. So the first one is a measurable map, which is, okay, let me change the pen. F from M to M, a measure preserving map. Measure preserving map means that the push forward of the measure mu with respect to F is just mu, that F star mu is equal to mu. And you need a map from M to GLDR, measurable. And a linear cocycles defined by A over F is a skew product map, which is this map F. Given XV, you associate as the first coordinate f of x, and at the second coordinate, you apply A of x, which is a matrix, and apply to V. So the idea behind is just, it's a kind of generalization of what we know of derivative. So for derivative, you know that if you have a local diffeomorphisms, so if on the manifold, if the manifold is nice, let's say if M is a torus, PD, you know that the derivative is just at any point can be seen as a linear map, GLD. And the idea behind linear cocycle is the idea of separating the map F with the derivatives. Here we have two objects, F and A. So let's see. We can iterate this function F, and the second iterate is given by F and F2 of XV. This is nothing else that f of x, ax applied to V, right? And you apply the formula at the first coordinate, you get the second iteration of little f, and at the second coordinate, you apply A to f of x and apply it to the vector axv. So you can iterate this for any n. So for any n, you get this formula fn of x is equal to fn x, a and x applied to V, right? And a and x stand for, this is a definition, it's the product of these matrices along the trajectory of the point x, right? And the natural question is, what can we say about the norm of an? So in dynamical system, usually we are interested on the long-term behavior of a system. Here, we want to know what happens when n goes to infinity of the norm. And the answer is given by the following theorem of Furstenberg-Kesten that state that if you start with any invariant measure, probably measure mu on M, such that the logarithm of the norm of A is integrable, then this limit exists for mu almost every x. Here I'm using the operator norm, but any norm would be fine. I mean, if you take a matrix B in GLD R, you can see that the norm, you can compute the operator norm, the supremum of BV over the norm of V for vectors that are non-zero, right? So what is good about this operator norm is that it's submultiplicative. So a norm of B1, B2 is always less or equal than the norm of B1 times the norm of B2. So when you put the logarithm, you get a subadditive function. So you are able to apply the subadditive ergodic theory to prove this. So lambda of x exists for mu almost every x, and it's called Lyapunov exponent function. This is the Lyapunov exponent for the cocycle. So Lyapunov exponent, and lambda is invariant, meaning that you have lambda composed with f is equal to lambda mu almost everywhere, almost every x, and that implies that if you start with an ergodic measure, the lambda is constant, almost the lambda is constant. So this is lambda is measurable and f invariant. Therefore, if mu is ergodic, then lambda is constant. Ergodicity, I didn't define what ergodicity means, but you can think of ergodicity, a system being ergodic if any invariant function is constant. You can take this as a definition. Okay, so next I will try to introduce a nice class of cocycle that are widely studied and very well understood, that called uniform hyperbolic cocycle. And Luciana mentioned also about uniform hyperbolic cocycle in her talk. It was very clear. So here we start with a compact metric space M and a homeomorphisms on M, F. So you consider continuous map A is continuous and take the cocycle generated by A over F, given by XV, F of X, A of F, AX applied to V. So you say that this cocycle is uniformly hyperbolic if you can find constant C and lambda, C positive lambda between 0, 1, such that for every X in M, you have transversal line ES of X, EU of X that are invariant by the fiber map A of X, and satisfy if you restrict AN of X in the stable bundle. I'm using this word, I identify what is stable bundle, but you can think of ES of X as stable and EU of X as unstable because of the following estimate here. AN of X restrict to ES of X is exponentially contracting, and AN of X restrict to EU of X is exponentially expanding. So you have some subspace here, ES of X, and the other subspace here, EU of X. So this is exponentially expanding vector. Vector that lie in EU of X are stretched by a factor lambda and 1 over lambda, sorry, and vector in ES of X are contracted by the factor lambda. In everything else in between, trajectory are going to infinite, either in the past or in the future. So this is a very nice definition, but it is very difficult to use because of you have to prove that a cocycle is uniform hyperbolic. You have to find the subspaces, the candidate for the subspaces, and also you have to check that this estimate holds. But for SL2 cocycle, we have a very nice characterization of SL2 cocycle. If you do to your cause, if F is a linear cocycle defined by a continuous map A from M to SL2R over homeomorphisms, you said that the cocycle uniform hyperbolic if the norm grows exponentially. So you just need to check that this is true for every X and N, and you can conclude that it is uniformly hyperbolic. All right. Okay. So next I will talk about Schrödinger cocycles, and I will tell you what this has to do with linear cocycles. So a Shrödinger equation is a partial differential equation with 4 variables. You have 3 space variables and and time, and usually it's very difficult to solve, it's very complicated to solve. What people do in general is that they look at the stationary Schrödinger equation, and the stationary Schrödinger equation means that time does not exist, so you just restrict to the 3 space variable, and still it's very complicated. And at the end, what you do is that you try to look at the one-dimensional case, which is an ODE, and still it's difficult. You try to discretize. So you end up with what we call one-dimensional discrete Schrödinger equation. One-dimensional discrete Schrödinger equation. So this is a little bit of story, but okay. So one-dimensional Schrödinger equation is defined in L2. I will consider the operator H. Usually in classical mechanics, H stands for energy. H is the Hamiltonian. And things that are scalar in classical mechanics become linear operator in quantum mechanics. So H is a linear operator, which is defined in L2, from L2 to L2. L2 is a space of sequence that are square summable. So given a sequence U, which is a UN, and in Z, you associate HU, which is given by, in coordinate, UN plus 1 minus UN minus 1, plus UN minus 1 plus VN UN, and in Z. So this is called the Schrödinger operator associated to the sequence Vn. So you give me a sequence, and I build the Schrödinger equation associated to Vn. So this term here represents the discrete Laplacian. This is a discrete Laplacian. Discrete Laplacian operator. Laplacian. So this is a second order difference equation because it involves terms of the sequence from n plus 1 to n minus 1. So the difference is 2. It's a second order difference equation. So it's formally written here. So you start with L2, which is a space of sequence that are square summable, and give me a sequence, a bounded sequence in R, and you look at the associated Schrödinger equation, that operator that is given by this form. And Vn is called the potential. The reason being is that in the physical context, Vn is actually the potential energy. So there are different problems. There are many problems depending on how to obtain the Vn. For us today, Vn will be dynamically defined. Dynamically defined means that you start with a dynamical system, which is a measure preserving map f from m to m, and you take a function v from m to r, which is called the potential, and you define Vn to be v of f of n. So you have x here. You look at the trajectory of x here. You get f of x, f square of x, so on, till fn of x. So Vn is v at this point, fn of x, where v is a map from m to r. And there are two cases that are very famous. That the one is a random Schrödinger equation. The difference also is how to get Vn. So the first case is, in this case of dynamically defined potential, you have two cases, which is a random Schrödinger equation, random Schrödinger, and the other one is the quasi-periodic Schrödinger, So in the random Schrödinger case, the Vn are random variable. So your space M is a shifted space. M is a shifted space. Is a space of sequences in X, and F is a shift map. I didn't put it here, but F here is the shift map. Shift map is the map that shift the sequence 1 unit to the left, and V is a map from M to R that depend only on the 0 coordinate. What does it mean? It means that you have a function defined from X to R, right? And V is induced by this function. From M to R, give me a sequence Xn in M and in Z index. This is bilateral sequence, and you associate V of Xn is just little v of x0. Right? In this case, we are talking about random Schrodinger cocycle. And the other cases is quasi-periodic Schrodinger. And this is the most famous because it involves a lot of beautiful mathematics. There are many people working on these cases, Schrodinger, quasi-periodic Schrodinger. So you can think of, you start with your space. The ambient space is a torus, but you can think of S1, M. Can think of M is equal to F1. You take F to be an irrational rotation on the circle, irrational rotation, or rotation on the circle by an irrational angle, and you can think of V to be the cosine function. And even if in this simple situation where you start, where your manifold is the circle, your transformation is an irrational rotation, and the potential is a cosine function, it's hard enough. You can find in the literature, there are many work that has been done for these cases. So what are we interested in for random Schrodinger, for Schrodinger operator? So you have a linear operator in a Hilbert space. You are interested mostly on finding the eigenvalue of the linear operator. So you want to solve the eigenvalue equation that is given by this formula, HU equal EU, and E stand in the physical context. E is an energy. The eigenvalue correspond to energy of your quantum system. So you want to solve this equation, HU equal EU. You can write it in coordinates. So, but before that, let me just mention a result here that say that if you start with an ergodic system, so the spectrum is the same for almost all choices. I didn't make it clear in the definition, because if you see this, you fix X, let's say for some X, I didn't say which X. So a priori, your operator H depend on X, right? Because the potential is depend on X. So what this theorem is saying is that if your system is ergodic, the spectrum of your operator is equal to sigma for almost all choices, for mu almost everywhere, mu almost every X. This is very useful because you don't have to worry about which X I have chosen for the potential. So because you will end up with the same result. Okay, so let's move on. So you want to solve this equation, the eigenvalue equation. So the first thing you have to do is you should write it in coordinate. So in coordinate, it is given as follows. For any n in Z, you can write the Hamiltonian, the operator, the Schrodinger operator. You have un plus 1 plus un minus 1 plus Z potential un. This is the left hand side, and the right hand side is EUN. So you can move this term, all this term here, to the right, and you get un plus 1 is equal to E minus V Fn of X un minus 1. So as usual in the theory of ordinary differential equation, when you have a second order ordinary differential equation, you can always translate it to a first order by increasing the dimension. For instance, if you have this system X dot equal F of X, so you can call Y to be equal to X dot, sorry, X dot is equal to Y. and x dot dot become y dot. So second order ODE become first order system of ODE. So we'll do the same here. We'll try to the same hold for difference equation as well. So for difference equation, you can look at un plus 1 un, to consecutive value of u. You can write it in terms of a matrix and un minus 1 un. You can check, because if you apply this row to this column here, you get the same expression here, right? And if you apply the second row to this column here, you get un equal un. So I didn't do anything. I just rewrite the previous equation. So this is very beautiful, because this means that if I have two consecutive terms of the sequence, I can get any other sequence using this matrix, any other term using this matrix, right? So, and this suggests to consider this linear cocycle. You can consider this linear cocycle. Give me an energy E. I look at the Fe from M time R2. Why R2? Because this is a 2 by 2 matrix. And given xv, Fe of x v is equal to f of x. F is the dynamical system. This is the map that we have that generate the potential, right? And as a second coordinate, you have ax applied to v, where a is given by this matrix. Ae of y is Ae of y is E minus V of y minus 1, 1, 0, right? So what we have done so far. So we start with an eigenvalue equation. This is very difficult to solve. We translate it to a problem of finding trajectory of linear cocycle. So this is a problem that we know very well. We understood in dynamical system, in ergodic theory, to be more precise. So you can write it in this term, doesn't matter. You can call un to be un and un minus 1. And so what I'm saying is that fix any initial condition u1, u0. So the solution are just trajectory of the linear cocycle that is defined by an of x. It is written in this term, very clear. So un is anex applied to u0. So to determine the trajectory, you need to understand the behavior of this guy here. But we know a little bit about this guy because this is a linear cocycle. So we know Furstenberg-Keston theorem. You can look at the Lyapunov exponent associated to this, right? So you can apply Furstenberg-Keston theorem. So applying Furstenberg-Keston theorem, you get the Lyapunov exponent associated to the linear cocycle exists for me almost everywhere. So this will play as an indicator. This will be like an indicator for the spectrum. Okay, so first of all, we will analyze the case of uniform hyperbolic. We have already defined what uniform hyperbolic is. Now let me consider this set. So you have the set of points for which Fe is uniform hyperbolic, meaning that an e of x, because here we are in the SL2 case, this is bigger than some constant c, mu to the n, where mu is bigger than 1, right? This is the set of uniform hyperbolic, the set of energy for which the associated cocycle is uniformly hyperbolic. So if an energy is inside, if E is inside U, this means that the norm of the cocycles is exponentially growing. So there is no solution. It implies that no solution for this, for HU equal EU. For this particular energy, we don't have an eigenfunction. Why we don't have an eigenfunction? Because since the energy okay, I have 5 minutes left. So don't have solution because this is growing exponentially. So the Lyapunov exponent associated for this is positive. If E is in uniform hyperbolic, you have the Lyapunov exponent associated is positive. So this is the norm is growing very fast to infinity. So you have a direction for which the norm is uniformly expanding and another direction for which the norm is uniformly contracting in the future. And you know that sequence is L2 does not go to infinity. So there is no solution. So I will define two other sets. So this is explanation that I put here. In particular, the Lyapunov exponent is positive. There is another set that is the non-uniform hyperbolic ones. So these are the set of energy for which you have positive Lyapunov exponent, but it's not uniform. The associated cocycle is not uniform hyperbolic. So it turns out that if the cocycle is uniformly hyperbolic, so the Lyapunov exponent is positive. But if the Lyapunov exponent positive does not mean that the cocycle is uniform hyperbolic. So this set is relevant, is a relevant set. So we have also a third set, which is given by the set of energy for which the Lyapunov exponent is 0. And finally, the theorem is the following, the Johnson theorem. The spectrum of this operator is just equal to the non-uniform hyperbolic one union, the decision union with the 0 one. So this is the non-uniform hyperbolic set, and this is the set of energy for which the exponent, the Lyapunov exponent is 0. And the union of these two gives you the spectrum of this. So this is the end of the talk. There are some references here. This is a very nice reference if you are interested in the subject, David Damanik's. And for linear cocycles, this is the book by Marcel is good. And there are some other, if you want to check the proof. So, gracias.
Thank you, Yaya. Actually, you end up 3 minutes before time. So you did it.
no Facebook. Don't make it like this, like me. Don't make it. You should to say to me that you drop 3 minutes that I got to me.
I give it to you. I translated it. Okay.
We are interchanging time now.
So if you have question, now it's time to ask.
Yeah, now we open to questions. I don't know if anyone has any question. Well, I actually have a question. I understand the math.
Okay.
But we work together, right? But the problem I have is with the physics.
Okay.
So actually, what the Lyapunov exponents means, that do they have any physical meaning? Why it's important to study them in this kind of system?
It's a very interesting question. But if you see, in classical mechanics, object has very well-defined positions. So you can say this star is here. You can use the position and the momentum. And these two objects can localize the object, the momentum and the position. But in quantum mechanics, things are different because of the uncertainty principle of Heisenberg. So you cannot say this electron is in this specific position. Because if you know the position, you lose the momentum. If you have information on the momentum, so you lose information on the position. So these are the duality. So you have to accept. So basically, in quantum mechanics, any particle is essentially anywhere in the universe. So, and the Schrödinger equation describe the wave. I mean, if you solve the Schrödinger equation, you get the wave function, and the wave function, in some sense, the potential, the position in the momentum are encapsulated in the wave function. So you interest solutions, but you don't want any solution. Here I'm considering L2 solution because of the phenomena which is called the Anderson localization. What Anderson localization means is that if you're able to say this particle is in this region, you're talking about localization. So you want solution that behave like bounded in L2. And you want to, okay, your particle is in this region. This correspond in the physical context. This correspond having L2 solution. So completely localized means that you have a solution which is a Dirac mass, and which is impossible. You cannot get a Dirac mass.
Okay.
So the Lyapunov exponents are telling you what are the energy for which the equation have solution. So if the Lyapunov is positive, the Lyapunov exponent corresponding to an energy is positive, and the cocycle associated to that energy is uniformly hyperbolic. So you don't hope to get a solution, because it's like you are having this matrix 0, 0, 1/2. So you have a direction which is expanding and a direction which is contracting. So all trajectories, since solution are trajectories, all trajectories are bounded. Horizontal vector are expanded, that are going to infinity. Vertical vector are going to infinity, but in backward, in the future, and all other vector are growing to infinity, either in the future or in the past. So you don't have solution. So the other case is when the Lyapunov exponent is positive, but the cocycle is not uniformly hyperbolic. So this is maybe a little bit difficult to handle. And the third case is when the Lyapunov exponent is 0, so you get solution, because by the Oscillator Theorem, you have that 1/n logarithm of the norm of a n of x applied to any vector u is going to be, the limit here is going to be, if the Lyapunov exponent is 0, the limit is going to 0. So vector does not grow. And this is just un plus 1 and un minus 1 for any n. And if you start with any initial condition, let's say, so you have control on the norm of the vector. So you can have to find L2 solutions. So that's why people put L2, because of the localization phenomena of Anderson. I don't know if I answered the question.
Yeah, just give me one second.
Don't worry.
Sorry, my dog wanted to congratulate you for your talk.
Thank you. Thank you.
Oh, thank you very much. Actually, I asked this question because
I was talking here. The dog wants to ask you a question.
Oh my God. So yeah, actually, I asked you this question because all the time when I give a talk, they always say, and why do you study this? What's the application, right? Because it's something very pure math. So everyone is like, okay, but what did it work for? So
yeah,
I like this.
What? You made a response. What? Do you want to? What?
The other answer is okay. You have a linear operator in a very nice space, so you don't care about anything else. So you have a Hilbert space L2.
Yes.
So
Exactly.
What do you want more for now?
you don't have to expect anything else. You have a nice operator in some Hilbert space.
That's all that you want.
That's
okay.
that's true.
Okay, thank you very much, Yaya. Well,
Thank
actually,
you, Diana.
we end up early and we have 10-minute break, a coffee break. I know in Brazil there is lunch time. I don't know if you want to take a little. Well, I know that Yaya doesn't has lunch at this hour, but
yeah, I think I will eat lunch at 4 maybe. 4 o'clock. I haven't taken my breakfast yet, so.
Okay, so maybe you want to have some breakfast. Okay.
Yeah. So who is next?
Next is Vinicius. I see him is now with us.
Yeah, he's here.
Hello.
Hi, Vinicius.
Sorry for being late.
Don't worry. Vinicius is actually
problem.
Luciana's student.
Okay.
Yeah.
Hi, Vinicius.
Hello.
Nice to meet
guys.
you.
Nice to meet you.
And actually, I see that Jorge is here today. Jorge is a Costa Rican who's studying applied dynamical system biomathematics in the US, right? I don't know if I'm saying it correct. Maybe you can
Yes,
correct me, Jorge.
Hi, yes, I'm sorry. I have my camera off. I cannot put it on right now, but yes, I'm doing mathematical biology here in the US.
Okay.
I'll be talking tomorrow on some of the work on my dissertation.
Ah, cool. Nice to meet you.
Nice to meet you.
He actually is going to talk tomorrow in the modeling part of this session. So you all
cool.
are invited to continue tomorrow.
Thank you. See, we will be there.
Okay, so we have the recess now. Maybe if you want to have some lunch or breakfast. Yeah.
So I will stop sharing my screen.
Okay, that's nice. And
Okay.
we will come back. Okay, Costa Rican time is 9:50. Brazilian
Okay.
time, I think, is 12:50.
Yeah, it's 12.
Right? Yeah.
So yeah, 12:36 here. I don't know if I have the correct time.
Yeah.
Yeah, but
So
it's okay.
we come back in like 14 minutes for the next talk, which is Vinicius.
Yeah. Okay.
Okay.
Okay, thank you.
Okay.